Now, looking at the phase change, we can visually see when a solid becomes a liquid and a liquid becomes gas, but what's the fun in just looking at qualitative when we can do quantitative information? Because we all love calculations. For the most part, we're going to be focusing on water because it's kind of a standard, but this information does apply to any substance that can undergo a phase change, which is any substance. All right, so first we're looking at what's called specific heat because that substance needs to be able to transition between the solid, liquid, and gaseous state. What specific heat is, it's the amount of energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius or Kelvin. Remember, because Celsius and Kelvin increase by the same increments because we add 273 and that's it. It does not matter if you're which temperature unit you are working in. Now, this is considered what's called a thermal property, or the heat holding ability of that substance. If you have if a substance has a large or high specific heat, that means it takes a lot for that substance to actually take in that heat. And it's obtained slowly, and it will take a lot for it to transition between potential phases. This is very important in substances that we use around heat. So if you take a pan, like a cooking pan, right? The handle is made of a different substance than the pan itself because you want the handle to be cool enough for you to grab. And so it's going to be made of a substance that has a higher specific heat because it's going to take longer for it to heat up so that it doesn't transfer that heat to your hand. That is why cast iron pans, because they're all one metal, you have to have that rubber handle to take it off so that you don't burn yourself. Substances that have a small or a low specific heat are going to obtain their high temperatures quickly. That means they will transfer energy. It takes very little for them to heat up and then move that energy either onto another substance or change their state of matter. So the pot is going to be made up of a different metal that allows the heat to move through the metal into the food in which you are cooking. Right? So when you have that allows it to cook, and you're not wasting energy heating up the pan and then transferring it. So knowing the substances we are working with that heat transfer is very important. Now water has a very high heat capacity. We give it the standard of 1.0, but this is very important quality of water, especially in bodies of water that can freeze. So the surface of the water will freeze during the winter times, but below a certain depth, it actually maintains that temperature year round because of how much energy it takes for it to transfer heat around. And that what allows aquatic ecosystems to survive in varying degrees of outdoor temperatures. Looking closer at how we can use specific heat. It is a value that we can use in a calculation so we can quantify the energy that moves through a substance. It does have different symbols depending on the textbook or the person in which you're talking about. For the most common is going to be a C to represent that specific heat. Some people have used SH, some use H. Just know that they all mean the same thing. Water is our standard when we are looking at specific heat. If you notice, we have two different units here that we can use to measure energy. Calories versus joules. Joules is the SI unit for energy. However, in health medicine, calories, because that can be easily converted to food calories and energy within a biological system, tends to be more commonly used in those sciences. But it's an easy conversion because 1 calorie equals 4.184 joules. That's neat. And so we can do a conversion if necessary between the two different units of heat. Using our understanding the specific heat of a substance, we can measure that energy. So we have this equation. I call it MCAT because MC, that delta looks like an A and then a T. This allows us to measure how much heat is absorbed or lost with a temperature change. So we could be looking at a phase change, increasing or decreasing the temperature. Q is the variable we use to represent heat or energy. Again, that's going to be your calories or your joules. M is mass, C is specific heat, and then delta T is the change in energy. So change means we're going to have an initial and a final energy. When you have your Q value, you can have it as a positive or a negative value. If you have a negative Q, that means it is an exothermic process. That heat was lost. It does not mean it's like a negative number. It's just telling us the direction the heat is going. If you have a positive Q, that is an endothermic process, which means heat had to be gained to allow that process to occur, that temperature change to occur. So when we look at a problem, we use final minus initial, whether or not we get a negative or a positive value, because that's just telling us the direction heat is moving. So let's practice this math. It's so exciting. Going through the same process we always do, nothing's new here. So we're going to calculate the calories needed. I don't like that released because it's not. The calories needed when you have 25 grams of water that is heated from 15 degrees Celsius to 45 degrees Celsius. So I'm going to write all my information down. So I'm looking for Q in calories. My mass is 25 grams. I'm working with water. So water, when we say water, we're saying liquid water. Otherwise, we'd say ice or steam for different phases changes. So we know the standard of liquid water is 1 calorie per gram degrees Celsius or Kelvin, doesn't matter. And then we're going to have our change in temperature. So looking at our change in temperature, I have T initial versus T final. So I have 45 minus 15 gives us 30. I'm going to put a decimal point there so that we have that significant zero based off addition subtraction rules, right? So you want to make sure that you're following through with consistent rules. So we have a change of 13 degrees Celsius. Setting this up, Q equals MC delta T. So Q equals 25 grams times 1.00 calories per grams degrees Celsius times the temperature change of 30 degrees Celsius. So the way that the specific heat unit works is calories is in the numerator, grams is in the denominator. So grams can cancel out because that 25 grams is also technically in the numerator. Degrees Celsius cancels out, leaving us with calories. So we're going to solve that Q. And we're going to get 750. Looking at our significant figures, we have 2. This is not, our specific heat does not count for sig figs because it's a standard value that we all agree on in the scientific community. And we need to look at temperature. And we are looking at temperature after the change in temperature because that mathematical equation has already been done. Okay, I'm going to say that again. We're looking at the significant figures of the change in temperature, not the temperatures recorded in the problem above. Because this was an addition subtraction problem, it follows the decimal rule. And then down here, this is a multiplication division problem. So it's going to do the lowest sig figs. So this is the number we need to look at when recording our significant figures. Both have 2. So the number I wrote, 750 calories without a decimal, is correct. If you want, you can always do 7.5 times 10 to the 2 calories as well. So we have been looking at quantifying the energy that is going into a heating or cooling curve. So remember, when we are looking at these curves, we go from a solid to a liquid in transition, liquid to a solid, and so forth. With the specific heat is looking at that change in temperature. So here we have our solid line. I don't know why I'm writing an S like that. We have our initial temperature to the final temperature. So we are looking at the one state of matter and the change in temperature. So that is going to be our MCAT calculation. And we'll do this, we could do the same thing for a liquid and for a solid. But what we have to remember is that the x-axis is always measuring the amount of energy going into or out of that system. So even though MCAT, or the change of temperature, is looking at how the solid is changing temperature, liquid changing temperature, gas changing temperature, it's not taking into account the phase change. So in these plateaus where we have our phase change, we still are inputting energy into the system. It's just the energy is no longer going to a temperature increase or increase in kinetic energy. We're now focusing on that energy to breaking those intermolecular forces. Therefore, we need to account for the amount of energy it takes to break those intermolecular forces. Each plateau has a different amount of energy that is required. Looking at this first plateau, this is called the heat of fusion, or your HF. So I'm going to erase this here. So we are looking at HF. What this is the amount of energy, Q, needed to melt or freeze a substance. So melt means the energy required to break the intermolecular forces between a solid and a liquid. If we're going through a cooling curve, it's the amount of energy needed to be removed to go from a liquid to a solid. The value we use to represent heat of fusion is a measured number because different sources use different values. So this is going to count towards our sig figs in the final answer when we use this calculation. So the amount of energy in that transition is HF, and we're going to be using 80 decimal calories per gram. So we can calculate the amount of energy that's going to occur in that phase change. If we use that same amount of mass that we used in our previous problem to discuss this transition or the increasing temperature, we can figure out what this phase change is. So Q equals MHF. We had said that M was 25 grams and HF is 80 calories per gram. So grams are going to cancel out, and we take 80 times 25, and we're going to get 2,000. Now for sig figs, this is where you'll have to go into scientific notation because we need two significant digits. So 2.0 times 10 to the third calories would give us that value. So if we're looking at this transition right here from a liquid to a solid or a solid to a liquid for 25 grams of that water, it would take 2,000 calories of energy to input that phase change. Okay, so going back and redrawing our graph. So for each of these slopes, so I have a solid, liquid, gas, because they are temperature related, we use that MCAT calculation. We had just talked about the heat of fusion, which is the transition from that solid to the liquid. So we have that Q equals MHF, where HF is 80 calories per gram. So now we're going to be looking at the next plateau. So with this next plateau, it is called the heat of vaporization, HV. So this is the amount of energy needed to vaporize or condense a substance. So the vaporize is how much energy needs to go into the transition from a liquid to a gas to break those intermolecular forces. To condense, how much energy needs to be released from a gas to a liquid. This requires a lot more energy because we are completely breaking the intermolecular forces. With HF, we're just disrupting some intermolecular forces or bonds because that liquid still has that close interaction. But to go from a liquid to a gas, that requires severing any interaction between particles. So the value for HV is significantly higher than that of HF. Again, this is a measured value because it is different for different sources. Similar setup, just using HV instead. All right, so we're going to do, I want to stick with our 25. All right, so how many calories for that 25 grams that we had discussed with our last two problems? So how much is that as we move through to the steam process? So remember our HF, our heat of fusion, was 2,000. So how much more energy does it take for the same amount of water to go from a liquid to a gas? So Q equals mHV. We're going to put our 25 grams in here. We're going to do 540 decimal. And we're going to get 13,500. So that is going to be 14,000 calories. So much more energy is required to completely break the intermolecular forces between those particles than to disrupt some of them. So this is why steam burns are very dangerous, is because the amount of energy in that phase change is significant. But also why you can get a freezer burn, because there's still energy in that transition state, but they're nowhere near what a steam burn can be. All right, so looking at a problem and not knowing what calculations we need to use, so I am going to show you a couple different ways in which you can figure this out. For those of you who are visual, bringing the heating/cooling curve with you can help you represent what type of calculations we're going to be using. So I know that on the slopes I have my MCAT. I've got my phase change. From solid to liquid, liquid to gas. Okay. So now that I have that labeled, reading the problem and figuring out what's going on, this can give me a map to work with. How many calories? So we know calories is Q. Is released when we have 150 grams. So we know that we have our mass. We are working with water, so we know if we need the specific heat, that the specific heat of water is 1.00 grams per degree Celsius, is cooled from, here we have that temperature change, so 20.0 to 0.0 degrees Celsius, and freezes. So freezes tells me that we are undergoing the heat of fusion. All right, so I wrote all that down. Now, with two of these pieces that are our constants, our C and our HF, how did I know that they were there? What you can do is you can take a look at where are we working on this graph. So I know I'm starting with water, and when we use the term water, we're speaking about a liquid. That liquid is starting at 20 degrees Celsius, so it's above that freezing point. We cool it to 0 degrees Celsius, which we know is the freezing point of water, and it's going to freeze. So it's going through that phase change of the liquid to a solid. All right, so that tells me I'm going to have to use my MCAT calculation and my heat of fusion calculation, which is where those two constants come from. All right, so we're going to have to do two sets of calculations. Doesn't matter which one you do first. So if I have my MCAT, I've got my mass, I need my delta T. Remember, we want to calculate our delta T first so that we satisfy our addition subtraction math process first. So we always take final minus initial. So our final is 0 degrees Celsius, our initial is 20 degrees Celsius. So when we subtract those two, it's going to be 20.0. Remember, it's addition subtraction rules, so we go based off decimal point. So we're going to have negative 20.0 degrees Celsius. Celsius cancels out, grams cancels out. Alrighty, so we have negative 3,000 calories. I'm going to leave it at that. If you want to go to sig figs, you can. So that's going to be 3.0 times 10 to the third calories. All the negative tells us is that this is an exothermic process. So heat is being released. That's it. Now I'm going to do my Q equals MHF. So it's the same mass of water that is undergoing a phase change of freezing. And I get 12,000 calories, right? And so that already has the appropriate number of sig figs. So if you want to put it to scientific notation, you can. It is up to you. All right, so we've got the transition of the energy with our MCAT and our HF calculations. So now we need to add them together. And we add them together using the addition subtraction rules. So at this point, we've had to use a couple different rules. We had to use addition subtraction for our delta T. That gave us the 3 sig figs in our final answer. Then we had to use our multiplication division for both our Q calculations. We are actually going to be ending up and using addition subtraction for our final Q. Here, if you want to multiply or add within scientific notation, you can. If you just want to leave it as decimal numbers, that's okay as well. So we used a total of 15,000 calories in this transition. Yep. I made a mistake there. So with that, technically it's negative 15,000 calories because it's an exothermic reaction, but you don't have to put that as long as you understand that energy was released into the environment.